All right, good morning. Here we are for another lovely lesson on CENG 3306 Mechanics of Materials. And this is going to be the last lesson that covers material that will be this is going to be the last lesson that will be covered on the exam number 2. That will be on tomorrow, actually, on Thursday evening from 6 to 9 p.m. And again, that is, of course, for any students watching this this semester. If you're checking this out in later semesters, please disregard that. All right, so let's get started. Today we're going to be working with combined loading, and this is covered in section 8.2 of the Hibbler text, and we have a few lesson objectives, learning objectives. First, we wish to learn how to calculate external reactions and internal forces on a 3D structure. Second, use elastic equations for axial, torsional, and pressure stresses to calculate the state of stress at a point. And finally, 3, calculate principal stresses and maximum in-plane shear stress. So let's look at this. Let me make sure we are recording, we are good. Always going to be paranoid about that. All right, so let's see. First of all, I would like to go through and do a bit of a review of basically some tools in our toolkit from previous lectures that we will need to use for our combined tools. Has 2 L's, not 3. Tools from previous lectures. All right, so let's see. First of all, we're going to have axial load, our equation for axial load. Next, we're going to have our equation for circular torsion. And finally, I'm going to need the equation for pressure vessels. So pressure vessel, cylindrical pressure vessel. Oh, I cannot spell vessel today. I'm having all sorts of trouble spelling today. Caffeine and evidently hasn't kicked in yet. Cylindrical pressure vessels. Okay. Now, these are only 3 examples of types of loading we can have. We will learn about further ones as we go through the semester, especially shear and bending, which we'll see in terms of beams. But so again, these aren't the 3 only types of loading, but they're just types of loading that I'm going to use as an example of how to combine different kinds of loading together. So here, our normal stress from axial loading is simply P over A. Our shear stress from torsion, taut equals T rho over J, T rho over J. And cylindrical pressure vessels we have longitudinal and hoop stress. Hoop stress, sigma H, is PR over 2T. And sorry, I got that wrong. I'm supposed to put the right ones with the right ones. Yes, sorry. So this is sigma L. Our longitudinal stress is PR over 2T. And our hoop stress is PR over T. If we remember in a cylindrical pressure vessel, our hoop stress is twice our longitudinal stress. So I'm going to work through an example and to illustrate how this works together. Okay. Basically, all I'm going to do today is work through a couple examples of how to handle combined loading. So let me draw this first combined example out. Example 1. Let me just go ahead and label it example 1 just to be more formal, because we are oh so formal in this class. We are the strictest, most formal people imaginable. Okay, anyway, so I'm going to have a solid shaft, a cylindrical solid shaft with a variety of loading on it. So I have a cylindrical shaft like this. And let's see, I'm gonna show the stress element that we're gonna be looking at. We are going to be looking at a stress element, say right here, A. Stress element A here. And this thing is going to have a radius of 2 inches. And this is a solid shaft, so we don't have to worry at all about things like holes and things like that. So I'll just go ahead and tell you, reiterate that this is a solid shaft. A solid shaft made of one material, nothing really strange going on. Everything's nice and boring. Nice and boring and happy. Okay, so let me show you the loadings that are on here. So previously we have had axial load and we have had torsion, but we haven't had them together. So let's look at that. I'm going to have a 50 kip axial load on here on either end. So it is loaded centrically, but it's not necessarily a CAL member because a CAL member would have only the axial load on it. So we're going to have 50 kips axial load here. And then I am going to have a 40 kip inch torsion applied on either end. 40 kip inch and 40 kip inch. Kip inch. Now, let's see. I'm going to label sides. I'm going to call the front end A and the back end B. Front end A and back end B. And I would also like to take a moment to label some axes. Basically, okay, so this is running into itself a little, but that's okay. What you need to know is along the axis of the member, that is going to be our x-axis. So I'm going to let this be x-axis. I'm going to let this be the y-axis. And I'm going to let this be the z-axis. And so, in the case of combined loading, we could have loading actually at different axes. We could have an my, which is about a moment about the y-axis. We could have an mz, which is a moment about the z-axis. And we could have an mx, which is a moment about the x-axis. However, in this case, all we have is the mx, the moment about the x-axis. This one is equal to tx, and this is the 40 kip inch moment. And so basically here we're going to have both a fx and an mx, a moment about the x-axis and a force along the x-axis. Okay. Questions on that? All right. So next I need to work through a series of steps. The first step will be to find the reactions at the fixed end. Okay, so find reactions at the fixed end. And the fixed end is here. That's what this is sort of designating. This is saying that this is a fixed end and that we can have a variety of reactions here as need be. Okay. All right, let's see. So actually, let me just say this is the reaction Fx. So this is basically I have a moment, a force on the end on the A end, and then I have just the reaction on the B end there. All right, so find reactions at fixed end. Oh, I want to do this in blue. So the first step is to find the reactions of the fixed end. So here, so actually, you know what? Let me make a little. I think I jumped ahead of myself. Let me make clear how I'm getting these. I don't want to let me just say that I don't initially know these. So let me just call these initially TX and torsion X and FX here. So in reality, I would have to solve for these. Now, yes, I can obviously see what they're going to be, but there may be cases that I wouldn't know these right off the bat, that I actually have to do some math to find them. So let me just make clear that I'm having that initially I have some reactions that I don't know. So again, we have a solid shaft fixed on this end, and it has these loads applied on the A end, and I have these reactions on the B end. But we will get the same results I listed earlier, but I think I'll actually list how we are getting these. So if I do a sum of forces about the x-axis equals 0, I can do a sum of forces about the y-axis equals 0, and I can do a sum of forces about the z-axis equals 0, and I can do a sum of moments about the x-axis is equal to 0, a sum of moments about the y-axis is equal to 0, and a sum of moments about the z-axis is equal to 0. So you notice in these systems, we have 6 degrees of freedom. We have 6 equations of equilibrium we need to consider for a 3-dimensional object. As compared to our usual 2, we see when we're dealing with a 2-dimensional object. And this is going to be simply 50 kips minus fx equals 0. So this leads us to fx equals 0. Hello. And then I could say, okay, you know what? Let me just go ahead and recognize that I could have, I've shown the ones on here that'll actually appear, but there also could be others, a different force. There could be an x force, a y force, and a z force, and an x moment, a y moment, and a z moment on the reaction end. All right, so let's say this one, I would just simply have Fy. And since I have no other forces to resist this, Fy is going to be equal to 0. If I did a sum of forces in the z direction, I would get that I would have Fz, and there would be there are no other forces in the z-axis, so the Fz is simply going to be equal to 0. Next, I could do a sum of moments about the x-axis. I would get negative 40 kip inches, the applied load, plus Tx is equal to 0, and therefore Tx is equal to 40 kip inches counterclockwise. Counterclockwise. Oh, and sorry, I flubbed here again. Fx is 50 kips. Okay, and so this is just my is 0, mz is 0. There's no moments there either. It's just like this. Okay, so we now have our reactions, maybe spelled out a little bit. I know that was a little confusing. I probably shouldn't have written my values that I would get initially. If you're going to do this properly, you would start by just writing the reactions as variables and then solving for the Tx and the Fx as necessary to keep this thing in static equilibrium. Okay, next I'm going to determine the stress at point A. I'm going to determine the stress at point A. Determine stress at point A. Okay. And I'm going to have a little note here that will help figuring this out. So first note, A here lies in the xy plane. A lies in the xy plane. So if we go here, we can say this is, as drawn, this is a little bit, it's always hard to get this exactly right, but this was meant to be drawn so it was perfectly vertical. It's right on the side of the member. So the stress here is going to be right on the xy plane. Actually, sorry, I was meant to draw, let me go back there. No, that's okay. Yeah, A is on the xy plane because we're going to have forces in the along the x. That makes sense. The reason for that is because we're going to have a combination of torsion and axial force. So that doesn't have anything to do with how it was drawn. That just has to do with the loadings. All right here. Now let's see. Let's look at the axial. So let's look at the different loadings we're going to have. Let's first get the axial stress, or the stress caused by the axial load. And I'm going to have these. So let me just draw the element here. I'm just going to call this A. And then this will be the x-axis and the y-axis. And let's look at the loading on here. I'm going to have P and P, but let's look at the stresses, not the loads. So here, sigma x is equal to P over A is equal to, well, this is fairly easy to calculate, fairly trivial to calculate, equals 50 kips over pi over 2 times 2 inches squared. And this equals 3.98 KSI. So we have 3.9, oh, sorry, yes, just pi, derp. Yeah, sorry. Pi, not pi over 2, just pi. Sorry about that. I know how to calculate the area of a circle. Okay. 3.98 KSI. Next, I will consider torsion. So we have the stress generated by the axial force. Now I need to find the shear stress generated by the torsional force. You got that? Okay. Next, let's look at torsion and the shear stress therein. Torsion. So I need to draw a torque diagram here. Torque diagram. Torque diagram. And this is going to be a fairly trivial torque diagram. I'm just going to have A and B here. And let's see. This is actually going to be negative. So this is actually my 0 line. 0. It's actually just going to be down like this. It's actually, the whole thing is negative. So this is just negative 40 kip inches. And this is when going from A to B. Going from A to B. All right. So let's apply the torsional stress formula. Tau xy Tau xy is equal to the torsion T times the outer radius rho, or I shouldn't say the outer radius, just the radius of where you're taking stresses at, although in this case we're looking at the critical stress, that's going to be the maximum at the outer surface, over J, and this is then equal to 40 kip inches times 2 inches times the formula for the polar moment of inertia of a circle, pi over 2 times 2 inches all to the 4th power. And this equals 3.18 KSI. And so then our stress element here, we will have X and Y here. This will be our element A. And we're just going to have a stress like this. It's just going to be this value here. Like this, like this, like this, and like this. Positive shear stress. Yeah. tau is here again 3.18 KSI. Let's see. And there's a question whether it should be positive or not. Yes, just depending on how our coordinate system is defined. Okay. So I might need to check up on that in my notes. Okay. So moving forward. Like questions on that?
Just on the positive negative convention.
Yeah, I need to think about that. It's my notes say negative, but I need to think about that. It is a three-dimensional problem, and the signs are always a tricky thing. But
Maybe it was because we were taking shear, maybe we were taking cut it in or whatever it was.
okay. Anyway, combined. So now let's look at the combined loading. The combined loading. So let's see here. I'm going to have the same element here, but I'm just going to superimpose the two stress conditions on top of each other. Stress is combined by the simple principle of linear superposition, so you can just combine them together. Stresses acting on the same piece of material will just apply linearly, just directly on top of each other, just a simple summation. So this is going to be 3.18 KSI. And then we're going to have 3.98 KSI. Now we're going to need two points here. And I'm going to have my point H be 0, 3.18, 0, 3.18, and my V be 3.98, comma 3.98, comma negative 3.18. 3.98, comma negative 3.18. And finally, I am going to draw a Mohr circle. You know what, I'm just going to go ahead and do this on the next page because I have a little more room that way. Got that? Okay. So let me draw a Mohr circle in the XY plane. Mohr circle in the XY plane. Okay. So sigma average, let's find that. That's going to be the center of the circle. Is going to be sigma x plus sigma y over 2 is going to be equal to 3.98 KSI plus 0 over 2, which is going to be equal to simply 1.99 KSI. The R, let me actually list all the formulas I'm going to need. R is going to be, of course, we're very familiar with these formulas by now. Going to be equal to sigma x minus sigma y over 2 squared plus tau xy squared. And then the principal stresses, sigma 1, comma 2, are going to be equal to sigma average plus or minus r. All right, so let's get that. This is going to be the square root of 3.98 minus 0 over 2 squared plus 3.18 squared. And this will equal 3.75 KSI, which is also equal to tau max. And then let's find the principal stresses. So that's just going to lead to, you know what, I think you can do subtraction. Sigma 1 is going to be 5.74 KSI in tension, and sigma 2 is going to be equal to 1.76 KSI, this one in compression. So it'll actually be negative. So then Moore's circle will look like this. Here, with our sigma and our tau, sigma KSI, and tau also KSI. And now let's plot the circle. So let's see here. Another potato of a Moore circle. And now our H is going to be here. So notice our H is our pure torsional state. So it has no normal stress, only shear stress. This is our H point. But it's not. But notice our point of pure torsion is not actually our point of maximum shear stress. Our point of maximum shear stress is actually going to be up here. And so the diameter is formed down here. And this is V, which is the 3.98 comma negative 3.18. And these are our sigma 1 and sigma 2 values here. And that's a very crudely drawn Moore circle. Okay. So I have one more example I want to work through today. We're going to have a shorter lecture today just due to the lecture schedule and exam coming up, etc. And like I mentioned, this will be the last material which will be on exam number 2 for students taking this course this semester. All right, so let's look at example 2. Let's consider example 2. Example dos. Okay, so let's see. This time I'm going to do something with a hole in it. I'm going to have a hollow cylinder. Like this. Like this. Like here. With a drilled hole through the middle. Going all the way along the shaft. Okay, and now I'm going to tell you that this thing has an outer radius of 57.5 millimeters and an inner radius of 52.5 millimeters. So we've removed the vast majority of the cross section, 52.5 millimeters. Now, the reason this is so thin is because this is actually a pressure vessel. Isn't that lovely? So this thing is going to have an internal pressure. An internal pressure of 10 megapascals. So that's actually going to be one of our loadings. And let us say that this is I'm also going to have some torque on this. So this is going to be 600 pi Newton meters and 600 pi Newton meters over here. And let me show you I'll give you the dimensions on this. This thing is going to be 245 centimeters long. And then our stress element is going to be here, point A. However, I think I will make a point to draw a cross-section to very clearly indicate where the stress element is. Like so. And so I'm going to have my axes here. Well, first the global, so you can see the axes on the 3D diagram here. I'm going to have X, Y, and Z. But at the cross section, I'm going to have Z here, and I'm going to have the Y here, and our little stress element is going to be here. Our A is here. Okay? So I am asking us to find, I want to find the state of stress at point A. Find the state of stress at point A. So find the state of stress at point A. So essentially what we have here is we have, I don't know why you would do this. This would be a very bizarre situation. I wouldn't recommend doing this. This seems like a very bad idea. We have a pressure vessel under a relatively, I'd have to do some calculations. 10 megapascals, I don't have a good internal concept of how much pressure that is. But anyway, if you have a pressure, we still have a vessel under pressure, and for some reason we've decided that it would be a great idea to apply a huge torsional load to this thing. So I don't know why you would do that. I think that seems like a very bad idea. I don't recommend applying large twisting loads to pressure vessels, but there you go. 700 psi.
700 psi? I might be wrong, but I think that's right.
So atmospheric pressure is how many psi? That's, I'm trying to remember atmospheric pressure. 60. That's, I'm thinking 62.4. That's the density of water. That's not right. No, it's. Oh, anyway, whatever. That's okay. So actually, you know what? I'm curious. Let's find out. Okay, so let me convert 10 megapascals. Just give me a minute. I'm pulling out my calculator here.
If I remember right, it's like 14.7 psi per kPa.
I'm converting this to atmospheres just for fun. Because I think in terms of atmospheres, because I live in an atmosphere. I spend most of my time in an atmosphere. Megapascal.
It's actually a pretty normal load for a drill string.
Let's see. So 10. Let me just do this.
Some differential pressure and torsion.
Yeah, I guess that would work for drilling. Yeah, that's an example that you might have with drilling.
I mean, this seems pretty normal in that case.
10 to the 6th pascals. Convert to units. Let's do pressure. Atmospheres, a little bit of a side note here. Okay, so that's 99 atmospheres, which, you know, for certain industrial applications, like for example drilling, this might be useful, but that's a very small. 245 centimeters seems rather short length for a drilling shaft, but whatever. So yes, we have a 600 pi Newton meter moment applied to this thing, but this thing is also pressurized to 99 atmospheres. So this seems like a very bad idea, but oh well, let's just not worry about that. I guess let's see what happens. We are here to see if this is a bad idea or not. We got to actually look at the stresses involved. Anyway, sorry. Sometimes I like to go aside and just sort of get realistic and say, wait, why would we actually do something like this? But anyway, this actually does have applications, especially things like drilling, and there are times that you'd have a pressure vessel that may be supporting some sort of load, and that load could be off-center, and that could generate a moment, and et cetera, et cetera. I'm sure we could contrive or find many applications where this does actually happen. Okay, so internal pressure. I want to calculate the stresses by internal pressure. So the basic methodology here, again, is we calculate the loads by each of the load conditions, and then we combine them together in one stress element, and then we run through a Moore circle to find the principal stresses. So let's see. First, we're going to check if the internal radius, first we're going to check if this is a thin-walled pressure vessel or not. Well, R internal over T is greater than or equal to 10. Is it? Let's check that. So this is what the condition we need to meet for it to be a thin wall pressure vessel. And so 52.5 millimeters over 5 millimeters It's only a 5 millimeter thickness wall. So this is 10.5, which is greater than 10. So therefore, indeed, this is a thin wall pressure vessel. This is indeed a thin wall pressure vessel. Got that? Okay. Now I want to find my stresses. So again, let us review for pressure stress. I'm going to have an element A, and if this is the X, this is the Y, I'm going to have stresses as follows. I'm going to have a sigma longitudinal along the x-axis and a sigma hoop along the y-axis. This just comes right out of how my axes are lined up. Sigma longitudinal and sigma hoop. So sigma longitudinal is going to be PR internal over 2T, and this equals, so let me just write the formulas first. Sigma hoop equals PRI over T, or simply 2 sigma L. Okay, so just plug and chug from here. This is 10 megapascals times 52.5 millimeters over 2 times 5 millimeters. And this equals 52.5 megapascals, and this is going to be actually in tension. So we'll need that. That's definitely going to be one of our critical elements. And this is simply twice this, which is 105 megapascals, also in tension. Also in tension. So next, let us consider torsion. So we have figured out our loading produced by pressure by a thin wall pressure vessel, and now let us look at torsion, torsional loading. So I'm going to have axes like this, and we remember that that torsion applies a pure shear loading. That doesn't mean the element is going to be entirely in that doesn't mean the entire member is going to be entirely in shear, but it applies a shear loading. Okay, so we're going to have, like this, a torsional loading here, torsion, 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 and torsion, and just a taw. And let's see, this is going to be a fun equation. T rho over J, which is equal to 600 pi, oh, that's 600 pi, not 60 pi. pi Newton meters for R torque. However, I will need to do a bit of unit conversion, so I'm going to say 1 meganewton over 10 to the 6 newtons. Okay? Because I want to get all this in megapascals. This is in megapascals, so I want to convert this to megapascals. Times 57.5, 57.5 millimeters per meter, or 57.5 millimeters. Let me write this out. Divided by 1,000 millimeters per meter. I gotta bake in a unit conversion into this thing. So I gotta use reasonably standard units. So over pi over 2, my polar moment of inertia, times, let's see, 57.5 over 1,000 meters to the 4th power, because we were given the diameter and the radius in millimeters, so I need to convert this to meters, minus 52.5 over 1,000 meters, also to the 4th power. And you plug and chug on that, you will get that the total shear stress is 20.8 megapascals, like so. So we'll need that. So now we have our pressure loadings and we have our torsional loadings. And the next step will be to find the combined loading. The final step will be to find the combined loading. Basically just applying more circle. Combined. So let us draw the stress element with the different loads superimposed on top of each other. I'll have element A here. And I am actually going to have loads in all the different, in every direction possible. Isn't that lovely? So I'm going to have X and Y normal stress, and I'm also going to have shear. So I'm going to have a, let me label the X and Y axis for clarity. X and Y. I'm going to have my X normal stress be equal to 52.5 megapascals. My Y is going to be equal to 105 megapascals, our hoop stress. And our shear is going to be equal to 20.8 megapascals, like so. And so we're going to need 2 points to create our Mohr's circle. And I'm going to use an H and a V. H is going to be 52.5, comma, negative 20.8. This point, the horizontal point's there, like right here. I'm going to use this one here. And then, let's see, 52.5, negative 20.8. And then V is going to be 105, comma, 20.8. So basically, sorry, this point here, the negative 52 point, the horizontal one here. Yeah. Okay. Anyway, 105, comma, 20.8. Okay, so we need negative 20.8. There. Okay. Now, so never mind that. B. So let's see. Yeah, there you go. Sorry, this is determined by this one, and V here is determined by this one. Helps if I reference that correctly. We're just using the two normal stresses along the positive X and Y axes. Okay, Mohr's circle next. Let me get my Mohr's circle stuff. Well, let's see. You know what we need? So I'm going to say my sigma average equals sigma x plus sigma y over 2. My tau max is equal to r is equal to the square root of sigma x minus sigma y over 2 squared plus tau xy squared. And sigma 1 or 2 equals sigma average plus r, or plus or minus r. And so running through these, this will give us 78.78 megapascals, and this will give us 33.43 megapascals. And this one, the principal stresses then, we will find that we have two principal stresses, 112, or 111, sorry, 0.2. 111.2 megapascals, that's going to be our sigma 1. megapascals in tension, and sigma 2 will be 44.8 megapascals, also in tension here. And then if I were to, I could use this to sketch more circle, which wouldn't be too bad. It would be like this, sigma and tau. The circle would be entirely within the tensile zone for normal stress. Another lovely perfect circle. My H and my V would be like this. H and V. And I would have sigma 1 and sigma 2 here. Sigma 1 and sigma 2. And that's our Mohr circle. All right, any questions on that? Okay. All right, so that'll do it for today. Again, this will be the last material that's covered on the exam for Thursday. This will be after I decided to quit a little bit early today because I wanted to just leave a break here. I didn't want to start up on shear and bending moment diagrams until tomorrow. So we will have a lecture tomorrow, a full-length lecture tomorrow, but that's going to be over shear and bending moment diagrams, which we'll not see on an exam until exam 3. So that'll do it for today. If you have any questions, feel free to email me. That will do it. I'll give you some more details in the exam tomorrow. And as always, thank you.